Hello, I welcome you to this introductory lecture on engineering, geology and rock mechanics. I am Ashutosh Kainthola, a faculty working with Banaras Hindu University, Department of Geology. Now, geology is a very old subject. We humans have used geological knowledge and geological material for our sustenance and survival. During Iron Age, we were mining iron ore. During Chalcolithic Age, we were mining copper. So throughout human history, we have retrieved material from Mother Earth. We have used the geological knowledge of building stone and excavation. Ancient Greeks, mainly Aristotle, Theophrastus, Pliny the Elder, they have written scriptures about geological time, geological processes and geological material. So it won't be an overstatement if I say geology or the use of geology or the existence or the prominence of geology is as old as the human history, human time. If not even Homo sapiens, I think even probably Neanderthals, they were using geological knowledge. Flint was being used to create tools during Stone Age. So geology is old. And what is geology? Geology is the studies related to Earth's interior, Earth's surface, structures present in Earth, the composition of Earth, the various dynamic processes which are taking place on the surface and inside the Earth. Now, we know that geology is quite old, geology is ancient. However, there is a branch of geology which is relatively new. We call it engineering geology. Now, what is engineering geology? Engineering geology is the engineering application of geological knowledge. So, if you are constructing a dam or constructing a tunnel, all these construction either take place on the Earth's surface or inside the Earth's surface. And they have to have geological inputs, be it the amount of stresses surrounding the construction or the parent material in which the construction will take place. So geology and the use of geological knowledge for civil construction is engineering geology. Again, like I've said, this is a very new field, let's say 100, 150 years old. Prior to this, limited geological inputs were incorporated while designing a tunnel or a dam. However, things changed. During the early 20th century, while underground excavation was taking place in Alps, there were instances of rock bursts, tunnel squeezing. Then the mining engineers and the geologists realized that, okay, there's more to it than just the composition of the rock material. There are stresses, there are different stress environments which affect the rock mass. Historically, it has been assumed that, okay, if it is rock, then construction would be much easier because rock is always stronger than soil mass. Technically, if a consolidated material, if it has a strength beyond 1 megapascal compressive strength, then it's classified as rock. So historically, it was always thought that construction in rock is easy, but things changed. Like I've just mentioned, the underground excavation in Alps, it made tunnel engineers realize that there can be issues related to stress environment during excavation. Then another major thing happened in 1928, the collapse of St. Francis Dam in California. The dam was designed by Mulholland, who was a self-trained engineer. Now, limited geological knowledge was available and people were actually not keen or were less inclined towards employing geological knowledge. If it appeared as a rock, if it appeared like a rock, then it was thought that, okay, this will have greater strength. So the left abutment of St. Francis Dam was found on a paleo landslide, and soon it collapsed and it led to death of more than 400 people. Then again in 1959 in France, Malpasse Dam, it was again a concrete gravity dam, it collapsed. The reason behind the collapse was the designers not employing the geological setup or the consequences of the prevalent geological setup. So what happened was the gneissic strata, the foliations of which were dipping downstream, and the heavy load resulting due to impoundment of water led to failure of the dam. So these instances made civil engineers, geotechnical engineers realize that, okay, we need to employ geological input, be it the mineral composition or the discontinuity orientation, while designing our dams, tunnels, roadways, highways. Now, you can either be an engineering geologist or a geotechnical engineer. Geotechnical engineers and engineering geologists, they work in the same lines. The difference arises from the fact that an engineering geologist does engineering using a geological base. On the contrary, a civil engineer, a geotechnical engineer, does geology using a civil engineering base. Now, what we actually deal with or what we want from this geological or geotechnical knowledge is to know, if I construct a building, a dam or a tunnel in a certain rock mass, then will it remain stable, or what would it require to remain stable, or what are the challenges I'll face while undertaking excavation. Now, what I want from my ground is, I want it to lead me or give me an easy excavation while I'm excavating, but after the completion of the excavation, after the completion of the structure, I want my rock mass, my ground to remain stable. So here my requirements from the ground are twofold. I want it to be weak when I'm excavating, and I want it to be self-supportive, or I want it to be stable after the work has been completed. Now, all these factors come down to the strength assessment. What is the mineralogical makeup of my material? In engineering geology, we mostly deal with rock mass, rock material. Now, rocks, they are an aggregate of minerals. They have certain strengths, they have certain composition. They may be prone to easy weathering, or they may in a way hinder or delay weathering depending upon their composition. But they are intact in nature. Rock material, the way I have used it till now, is intact rock mass. What engineering geologists, they have to study is rock mass, which is intact rock material, which is an aggregate of minerals, plus discontinuities. Discontinuities are joints, fractures, shear planes, faults, together with in situ stresses. So a rock mass would be your intact rock, your discontinuity planes, and your in situ stresses. The combination of these three components, it compiles what you call a rock mass. So rock mass can be weak, rock mass can be highly deformable, rock mass can be strong. We decide these three factors, its deformability, its strength, based on tests. The tests are done both in situ and inside the laboratory. Now, another thing that requires consideration is scale effect. So if my scale, if my area of interest, if my excavation domain, if my excavation parameter is quite small, then I only need to be concerned about the intact rock properties, the properties of the aggregate of mineral, the composite of different minerals. But if I increase my scale, then the properties of discontinuities, joint system, they are included, and they are crucial to decide the whole rock mass properties. There have been other well-defined classification schemes given by Banaras, which is rock mass rating, given by Barton, which is Q system, and one given by Hook, GSI, Geological Strength Index. We will cover these topics in another lecture, but for now we'll primarily focus on intact rock properties. So, like I just said, the assessment of both rock and rock mass properties is crucial for design of any excavation and construction. Before we go to the strength assessment, we first need to comprehend the difference between pressure and stress. So, what is pressure and what is stress, and how is pressure different from stress? Pressure is force per unit area. Similarly, stress is also force per unit area. But there is a fundamental difference between pressure and stress. Pressure is an external entity, while stress is internal. There is generation of stresses due to externally applied pressure. So, once you exert some external pressure, external load on a rock material, then there is a restoring environment generated inside the rock material, which is called stress. Again, pressure is scalar. On the contrary, stress is order to tensor. It has 9 different components. For pressure, you will have similar values in all the directions from a point, which may or may not be true for stress. And another important thing is, pressure is always acting perpendicular to a surface and is always compressive. On the contrary, stress can be compressive, tensile, or shear. Based on Cauchy's theorem, stress in a body at any point can be resolved into 3 mutually perpendicular stresses named as sigma 1, sigma 2, sigma 3. Sigma 1 being the maximum, sigma 3 being the minimum. Now, these axes are mutually perpendicular to each other, and the combination of these stresses generates normal and shear stress inside any plane in an element, in an object. Pressure leads to stress. This is external, while this is internal. Suppose there is a block of rock, I applied some force, some load, right? Then there will be certain restoring forces generated inside this body. Now, this is stress here. You are applying force here. This is force which is generating certain amount of stress. So, stress is internal. Now, how come it's different from pressure? Numerically, both are force divided by area. And in rock engineering geology, it's megapascal. Pascal being Newton per meter squared. So, numerically, they are both equal, but there is fundamental difference between pressure and stress, right? For pressure is always perpendicular, always acting perpendicular to the surface. On the contrary, stress, it can act at any plane, right? It doesn't need to be perpendicular to the plane. And another difference is pressure is scalar, while stress is tensor. So, for each plane you will have one normal component and 2 shear component, right? So, if this is your y axis, this is your z axis, and this is your x axis, and you have a cubic element here, right? So on this plane you'll have a normal stress component denoted by sigma y and two shear component. One would be directed towards x, it would be denoted as tau y x, and another one tau y z, and this is true for all the components. So this is the difference between stress and pressure. And again, you have one maximum principal stress, one minimum and one intermediate. These are the stresses which are acting on planes which have zero shear stress. They can be tensile in nature, compressive, or shear in nature. This stress leads to strain being deformation. So whenever there is stress acting in a rock material, there is development of strain, which is deformation, usually denoted in percentage as the ratio of change in either length or volume divided by original length of volume. So your strain can be axial, diametral, or volumetric strain. During the tests conducted, there is a peculiar plot of applied stress and the resulting strain for each rock. The gradient of the stress strain plot that we receive denotes the Young's modulus of the rock, which is the ratio of stress by strain. Numerically, it is the stress required by a rock for generation of unit strain. Different rock materials produce different stress strain curves. So once you start loading a rock material, there is generation of stress and the amount of stress gradually increases. The increased stress leads to increased strain. The strain gradually keeps on increasing with the increased stress up until it reaches a yield value where the deformation, the strain is non-recoverable. As in, if you remove the stress, the strain will persist. Then if you further increase the amount of stress, there will be a peak reached. At that place, rupture will take place. After this, the curve can either go up or go down. If the peak goes further up, then that is strain hardening behavior. That means more stress is required for generation of strain after reaching the peak, and if it goes down, then that is strain softening. As in, after the peak, even if you remove the stresses, there will be subsequent deformations. Here in this graph, you can see the deformation of ductile material. Ductile deformation takes place at great depths beneath the Earth's surface. Here, the confinement is considerable. So you can see once the yield is reached, there is plastic deformation. So that is why we have folds present on the Earth's crust. So based on the stress strain curve, you can either have elastic deformation, as in the strain will recover when you remove the stresses. You can have brittle deformation, as in you'll have rupture once the peak strength is reached, and then you have ductile deformation, deformation without any rupture after peak strength. As we have understood the difference between stress and pressure, now we can move to failure in rocks. Rocks, they fail when the surrounding stresses, their values go beyond the strength of the material. So if the strength of a material, let's say it's x, and the surrounding stresses are x plus 1, then the rocks will fail. This is a very generalized and simplistic statement. The mode of failure may be under compression, under tension, or under shear. So, depending upon the strength of the material or the compressive strength, tensile strength, or shear strength, you will have different failure modes and different failure strengths. Compressive strength would not be same as a tensile strength, which would not be same as the shear strength. Different stresses generate different failures. So, if we move on to the strength of the material again, we'll primarily focus on uniaxial compressive strength. This lecture will mostly deal with laboratory tests. We are not going to focus on in situ tests. So, first thing is uniaxial compressive strength or unconfined compressive strength. Well, all the tests in engineering, geology and rock mechanics are supposed to follow codes. The codes are given by, the testing procedures are given by ISRM, which is International Society for Rock Mechanics. There is Indian code, BIS code, and there are codes by ASTM, American Society for Testing of Materials. You may ask, why do we need these codes, these standard procedures? Well, the reason being that if tests at different locations and tests on different material, if they are conducted using the same code, then it's easier for us to correlate the properties, because we know we have followed the same procedure, same codes. That is why we follow codes. Here we are mostly following, in this lecture we'll mostly be following ISRM and Bureau of Indian Standard Codes. Now, the interesting part about ISRM is it was formed in the year 1962, and it was formed by German Professor Leopold Müller. After the failure of Malplace Dam in France in 1959, it was recognized that rock tests and their classification procedure, they need to be standardized. So, ISRM, it is the governing body as far as rock testing and rock classification schemes are concerned. So, UCS, it stands for uniaxial compressive strength or unconfined compressive strength. These tests are conducted on rock cylindrical cores. The cylindrical cores are usually retrieved from rotary drilling using diamond bits. Most of the projects where excavation will take place undertake borehole drilling to retrieve or recover subsurface information through rock cores. The rock cores come in different sizes, ranging from AQ, which has a diameter of 27 millimeter, going up to NQ, which is 54 millimeters. As per the prescribed code, the UCS test should be done on samples not less than 35 millimeter in diameter. In usual practice, NX size samples are the most common ones, and tests are conducted on them. Coming to the codes for UCS tests, the symbols used for denotion of or denoting UCS tests are QU, sigma U, sigma C, and the ASTM code for UCS test is ASTM 4543. The Indian code is IS 9143-1979, and the standard procedure is given in ISRM 1981. To sum it up, or in crux, UCS test is axial loading of cylindrical core specimen when the core specimen is unconfined from the sides. The UCS strength or the uniaxial compressive strength of the rock material is calculated as the applied load divided by area being pi r square, r being the radius of the rock core. The apparatus required for testing the uniaxial compressive strength of the rock material requires a suitable loading machine which can load a sample at the rate of 0.5 to 1 MPa, MPa being megapascal per second. The discs used for loading should have a hardness not less than 30 Rockwell hardness, and the thickness of those discs should not be less than 55 millimeter. One important thing as in they should be really plain, and the length to height ratio of the sample should be between 2.5 to 3. So, if the diameter of your sample is 1 centimeter, its height should be 2.5 to 3 centimeters. This is crucial and this forms the norm for testing. Again, the specimen diameter should be at least 10 times the size of the largest grain in the rock. This should also be kept in mind while testing a rock material. And again, I've said it that again, the ends of the sample should be flat to within 0.02 millimeter and should not depart from perpendicularity to the axis of the specimen by more than 0.05 mm in 50 millimeter. Once the sample is loaded, there is generation of strain. The strain is axial one, as in there will be reduction in length of the material, there will be shortening in the length, and then you have radial strain, as in there will be increase in the diameter of the sample. And we use strain gauges to measure the strain generated axially and diametrically. Now, the strain measurements are used to compute the elastic modulus and the Poisson's ratio of the rock sample along with its UCS values. I have already mentioned that strain would be, for axial strain, it would be change in length divided by the original length, and radial strain would be change in diameter divided by the original diameter. So here in this picture you can see how the tests or how the failure looks like, and in the middle image there is a plot between the applied stress, which is force per unit area. Here it's the y-axis, and the strain, which is change in length divided by original length, which is the x-axis. Another thing that should be borne in mind that while testing the stress rate should be between 0.5 megapascals to 1 megapascal, and the specimen should be loaded in such a way at a constant rate that the failure will take place in about 5 to 15 minutes of loading. Another important thing is at least 3 to 5 samples must be tested. ISRM says 3, but BIS says 5. So you must test 3 to 5 samples to get the representative UCS values. The strain gauges, one tied axially, another tied diametrically, gives you they give the strain values. Now this strain gauges, they work on the principle of impedance, resistance. So when there is change in length, the resistivity changes, which signifies the strain generated. So you'll have an axial strain which would be much larger than the corresponding radial strain, as you can see in the image. And here the Poisson's ratio would be lateral or radial strain divided by axial strain, and your Young's modulus would be stress applied or the gradient of the stress strain curve for axial tests, or the gradient of the curve between axial strain and applied stresses. Young's modulus can be tangent modulus, secant modulus or average modulus. Tangent modulus is the curve of the line of the 50% area, as in you just select the middle 50% of the stress strain curve and its gradient, that is the tangent modulus. Average modulus is the modulus of the whole stress strain curve, while secant modulus is the gradient of origin of the curve and 50% length of the curve. So these are the three representations of the Young's modulus, and one should be careful, or one should be explicit in defining what sort of Young's modulus is it. Is it tangent modulus, is it secant modulus, or is it average modulus? Now this is the data presented by Hudson in his book Rock Mechanics Principles in Engineering Practices, 1989, and it depicts the UCS values of different rocks. You can see shale, which is a sedimentary rock, its UCS value goes up to 100 MPa, while quartzite, basalt, dolerite. Quartzite is a metamorphic rock. Basalt and dolerite are mafic igneous rocks. They have the maximum UCS values. Now UCS value is a function of the grain size, the rock type, and how many microfractures or cementation is present. So rocks which are fine grained, rocks which are well crystallized, that is igneous or metamorphic rocks, they usually have a higher compressive strength as against fissile sedimentary rocks. Now here is a problem that I would want you to solve. Here the diameter, the length and the peak load are mentioned. You just need to calculate the UCS of the rock sample. UCS is load at failure divided by the cross-sectional area. Now it may happen that the core sample that you have may vary in its diameter. Usually all the tests as prescribed by ISRM are standardized for 50 centimeter cores. Then there is this correlation which helps you normalize your strength for core samples of 50 millimeter diameter. So we'll see a live demonstration of the UCS test now. Now we shall move to tensile strength. Tensile strength is the strength of the material that fails when the stresses are tensile in nature. Usually the tensile strength is quite low when compared against the compressive strength. The codes that we need to follow for tensile strength are given in ISRM 1978. The Indian code is IS 10082-1981 and the ASTM code is ASTM 2008B. There is a requirement for tensile strength in most of the excavations. It is used as an input parameters together with UCS in rock mass classification and Q system. So there are various avenues where tensile strength of the material is employed. Now the actual problem for doing the direct tensile strength, the test for UCS that we did was direct in nature. You were directly loading a sample under compression. However, conducting direct tensile strength tests on rock samples is difficult. You have a difficult in gripping the specimen and then applying the load, axial load without any eccentricity, it's a problem. So instead of conducting direct tensile tests, we conduct indirect tensile tests, and we conduct that using a cage called Brazilian cage. It's called a Brazilian cage because it was designed in Brazil. For the Brazilian testing of rock material, usually NX size core samples which are 54 millimeter in diameter are preferred. The thickness of the NX size core sample should be half of the diameter, that is around 26 millimeter. However, ASTM allows a thickness by diameter ratio of 0.02 to 0.75, and the two steel jaws will be in contact with the specimen over an arc length that subtends 10 degrees at the center when failure occurs. The two steel jaws of the Brazilian cage, right? Another thing that is crucial here is the rate of loading. If you have a higher, swifter rate of loading, the load taken by the sample would be higher as against a slower loading rate. Here in this image you can see the specimen, the cage, both upper jaw and the lower jaw. So you have a half ball bearing on the upper end on which the load is applied, right? And the load at which the failure takes place gives the tensile strength, or sigma T, which is equal to 2P by pi dt. Here P is the load at failure, D is the diameter of the sample, T is the thickness of the disc. Ideally, for an accepted Brazilian tensile strength test, the fracture plane should be parallel to the direction of the applied stress, and there should not be any indentation in the sample. So here the image to your left is a desirable mode of failure, and image to your right shows certain amount of indentation before failure. So this mode of failure is undesirable for Brazilian tests. Now these are the different UCS values and tensile strength values for different rocks that have been tested by Goodman. You can see the ratio between UCS for granodiorite and for volcanic ash. So in this data, the ratio of UCS by tensile strength ranges between 10 to 15.9. So you can expect that the ratio, the disparity between UCS and tensile strength, it can go as much as 10 times to 15 times. But a good estimate that is generally used during the preliminary stage of design is 1/10, or between 1/8 and 1/12. So if you have a UCS of 10 MPa, you can safely assume that it should be around 1 MPa, the tensile strength.